To design bridges to resist seismic forces, you're right, it is a big subject right now. Probably the foundation issues are the biggest in many of our cases. The liquefaction and some of the just poor soils that exist in Western Oregon in particular. They actually drive the cost of seismic design. It is a big process. The geotechnical part of this is huge, and then you have geotechnical engineers who are specialized in the seismic behavior of the soils and in investigating soils out in place to see what they can and can't do with them. And then on the superstructure side, the bridge structural engineers also, some are specialized pretty heavily in seismic as well. Putting it all together is quite a task. So we talked about finite element models earlier. So now you're taking that same model and applying the shaking basically from the ground moving to that model, and then looking at the stresses and the response of the structure then. So typically a bridge superstructure interfaces with a substructure through a thing called a bearing, actually through a series of bearings, typically one under each girder line. Those bearings, in some cases there are some sophisticated types of bearings called isolation bearings, which are actually designed to help the structure withstand the earthquake with lower forces by altering its dynamic response.
Seismic loading, that's going to come though from the bottom of the bridge. It's going to be transferred from the foundation up through the columns to the bearings into the superstructure. And it's going to be more complex. It could be a combination of vertical loads, horizontal loads. It could be a series of aftershocks. The bridge is going to be vibrating. So seismic loads can vary greatly between seismic events, and we learn from every major seismic event and change our codes because of it. So there's a lot to be learned in the field of seismic. When it comes to earthquakes, of course, California they've had some major earthquakes down there, and they had to replace many bridges. And then I think even some bridges they replaced, they get hit on a next earthquake or another earthquake. So we're learning all the time when it comes to earthquake loading. Liquefaction is when like a sandy material that typically would work just fine in everyday life. If there's an earthquake, that can tend to liquefy, and it won't support the bridge. And so it's just critical because you were counting on something to hold the bridge, and it's not. So that's why we have to do test boreholes and design, because what you've got at the bridge site is what you've got. You've got to design around it. And that's why the foundations for a seismically resilient bridge can be an extensive part of the cost of the bridge and just an extensive part of the construction of the bridge.
Seismic design, like many aspects of structural engineering, can be remarkably complex. At the same time, finding solid, simple methods to check complex problems can be grounding. In this video, we will look at some overarching concepts upon which you can build your understanding of earthquakes and how they affect structures. Let's begin by looking at the basics of seismic events. As tectonic plates slowly move, forces build up in the Earth's crust. Occasionally, these plates suddenly move to relieve these forces, causing the Earth to shake violently. As a fault ruptures, seismic waves radiate outward, creating strong ground motion that impacts bridges, buildings, and can be felt hundreds of miles away. During an earthquake, the Earth displaces in a variety of ways. A strike-slip fault manifests by predominantly horizontal displacement, as plates slide parallel to each other. This can cause roads to suddenly be misaligned, in addition to generating strong ground motion. In contrast, a normal fault is characterized by a downward drop on one side, creating a vertical displacement. Structures built across faults can sustain damage from both the permanent displacement and intense ground accelerations. To understand how earthquakes impact structures, let's look at this USGS animation. We see as the acceleration increases, the dynamic response of the building amplifies. Here we see a time history response of a multi-span truss bridge. The dynamic structural response to an earthquake is a function of ground motion, soil type, and structural characteristics. Because earthquakes release so much energy, it is economically unfeasible for structures to be undamaged after a large event. Engineers therefore design portions of the structure to be locally damaged, thereby absorbing large amounts of energy while leaving other areas undamaged. Expanding this concept of energy adsorption to a structural element under high-strain cyclic loading, engineers perform testing on actual bridge elements. They do this by pushing back and forth on the element and increasing force until it yields. They then continue the cyclic motion with slight force increases but causing large displacements. This generates hysteresis loops that plot force and displacement. If we draw a line along the elastic portion, then the inelastic portion, we can create the backbone curve. This tells engineers how much cyclic deformation a structural member can withstand. In this case, the red buckling restraint brace yields, dissipating seismic energy from the bridge. This leaves the bridge structure mostly undamaged after an earthquake, creating an effect like seismic isolators. The BRB can easily be replaced in preparation for the next earthquake. Looking at the hysteresis loops for a well-confined concrete column, we see lateral force does not degrade, even at a displacement upwards of 85 millimeters. This means the column carries substantial load even when heavily damaged. On the contrary, even though a poorly defined column initially carries substantial force, its strength degrades just after a few cycles. The area inside the hysteresis loop is the energy dissipated. The reality of ductility related to rebar tie spacing is dramatically shown in this photo from the 1971 San Fernando earthquake. The columns on the left had closely spaced ties. Though the concrete cover spalled off, the core remained intact. In contrast, the right column had largely spaced ties. Despite the large vertical bars, the concrete core deteriorated to the point it can no longer carry vertical load. These columns would exhibit behavior like the hysteresis loops we have been looking at. Dividing ultimate displacement by the yield displacement, engineers determine the ductility of the system and gain an understanding of how a structure will perform in an earthquake. The higher the ductility, the better. With a general understanding of earthquakes and how structures respond to them, we are now ready to dive into the process of seismic design, which has three main steps. Determine performance objectives, demand analysis, and capacity analysis. Understanding that structures are not designed to resist earthquakes without damage provides insight and wisdom and requires frank conversations with owners. Plotting performance and seismic intensity against cost, we see that as we increase performance and earthquake size, structure cost increases. Current AASHTO requirements are for collapse prevention at a 1,000-year return interval. For structures that demand higher levels of performance to protect public or private interests, a performance-based seismic design method may be worth implementing. Two primary methodologies exist for seismic design: the force-based method and displacement-based method. The AASHTO specification uses the latter. Both philosophies result in a capacity-designed structure that has sufficient ability to resist seismic forces and displacements. Capacity-designed means certain elements, usually columns and bridges, or beams and braces in buildings, are designed to yield in ductile fashion, and the other elements remain elastic. In bridges, this is often done at the column-to-bent cap interface. The key is to proportion the members such that energy adsorption occurs, but the structure does not collapse. In the force-based method, the force displacement curve is taken as linear. Engineers calculate displacement based on the unreduced seismic force, known as the elastic force. This force is then reduced by testing derived response modification coefficients R to obtain design yield forces and used to size members. Displacement demand is taken as the elastic demand. If engineers follow prescriptive lateral systems and details that ensure ductility, they can assume the displacement capacity is larger than the displacement demand. In the displacement-based method, displacement demand is taken as the elastic demand, like the previous method. However, the displacement capacity is explicitly calculated using a nonlinear static method, known as a pushover analysis. This is done by applying an increasing load to a structural model and capturing the nonlinear behavior of the material, such as yielding, crushing, and degradation at high strains. This provides a more realistic model of structural behavior in an earthquake. The model is then checked for strain and ductility limits to ensure it correlates to test data. If the displacement capacity is larger than the displacement demand, the structure is adequate. If not, member sizes and behavior are adjusted and reanalyzed. Looking closer at displacement-based design, we see the fundamental relationship requiring the displacement demand be lower than the displacement capacity. The AASHTO guide specifications for LRFD seismic bridge design provide the fundamental requirements and guidance for this design method. This specification provides 3 options to calculate elastic displacement demand depending on the level of structural complexity and importance: equivalent static analysis, elastic dynamic analysis, and nonlinear time history. Let's look at the uniform load approach of the equivalent static analysis method. We find displacement demand by calculating virtual displacements for an assumed load, bridge lateral stiffness and weight, period of vibration, static earthquake loading, and displacements and member forces. We begin by modeling the bridge in finite element software. While other analytical methods are available, this is the most effective tool. We then apply an assumed lateral load P0 on the bridge and find the lateral static displacements. It is convenient to set this as 1 kip per foot. We now have the model loaded, ready to analyze. After running the model, we see the static displacement V sub s at various points along the spans, and find the maximum displacement. To calculate the bridge's lateral stiffness K, we multiply the assumed load P0 by the bridge length L, divided by the maximum displacement, V sub s max. Weight is given by this relationship, but in practicality is often calculated by the sum of individual weights of specific bridge elements. Knowing weight and stiffness, we can calculate the fundamental period of vibration, T sub m, using this expression. Using a response spectrum, we use the period of vibration to find the design response spectral acceleration, S sub a. We now find the lateral seismic force by multiplying the design response spectral acceleration, S sub a, by the total bridge weight, divided by the length. We apply this to the bridge model to determine displacement demand and member forces. Looking at a single bent, we can see the displacement demand along the local axis of the beam. To determine the displacement capacity, we perform a pushover analysis. Also known as a nonlinear static analysis, it predicts the hysteretic behavior of the structure under cyclical earthquake loading. We do this by modeling the structure and apply an increasing force. As individual members start to yield, other members pick up additional load and yield. This creates a force displacement curve of the system, like a stress-strain diagram, adsorbing energy. The force and displacement are increased until the system becomes unstable. If the structure can still carry load at the target displacement and meets ductility requirements, it is considered acceptable. If not, member strengths and ductility are increased until it can. More specifically, the pushover analysis requires the following steps. Number 1, model the structure. Number 2, define expected material properties. Number 3, define section properties. Number 4, define hinge properties. Include nonlinear material behavior, such as crushing, yielding, and strength degradation. Number 5, analyze the model by increasing the lateral load, capturing the yielding, strength degradation, and stiffness change in each hinge, recording force and displacement, and push model to collapse. Number 6, determine the ductility index and acceptability for each hinge. Number 7, compare displacement demand to capacity. Software made by companies such as Midas, Larsa, and CSI are specifically made for the complex nature of this and other analyses.
Seismic design is really, it's an art in itself. And after every earthquake or every major earthquake, we change our standards because we learn from it. And every earthquake is different.
These 8 videos and their associated course materials are part of the historic mitigation agreed upon by the Oregon Department of Transportation and State Historic Preservation Office due to the removal of the historic Van Buren Bridge. They stem from the creative efforts of Preservation Works, faculty at Oregon State, the Oregon Department of Transportation, and the American Institute of Steel Construction. We thank the numerous people who have contributed their time and wisdom to making these videos. We hope these materials provide you, as the budding professional, insight into the impact engineering decisions have upon communities and individuals, exposure to an active construction site in an environmentally sensitive area, understanding of fundamental engineering principles, and an introduction to deep structural engineering topics.